OK, we just designed ECB mode. It's great. It helps us encrypt longer plain texts, but it is not IND-CPA secure. So we are now going to try to design something better that actually does provide IND-CPA security. So we already know that the main reason this didn't meet our security requirement is because it's deterministic. You encrypt the same thing 10 times, you get the same output 10 times. So to make it non-deterministic, I'm going to start adding some randomness. So if I throw in some random bits somewhere, maybe I can make it so that when I encrypt the same thing multiple times, the output is not the same every single time, thanks to some randomness that I add in, and it's different for every message that I encrypt. So let me try throwing in some randomness. So maybe instead of encrypting the plain text by itself, what if I take the plain text and I mix it up a little bit using some randomness? So now this input to the block cipher is not just the plain text, but it's the plain text XORed with some random string. So this little symbol is XOR. This is saying I will take the plain text, XOR it with the so-called initialization vector, which is some random bit string different for every encryption. Now if I pass this through the encryption block, the ciphertext should look different every single time. If I encrypt the same black pixel 10 different times, I will pass in the same plain text, but this will be different all 10 times. So the ciphertext should also come out different. So I'm slowly fixing the problem with the penguin from earlier. So this is good. Now my first ciphertext is going to be different every time, but I still haven't solved any of these other problems. If the second block of plain text is the same, that's still the same, and same here. So I've added randomness to the first part of this message, but not these later parts. So I should keep going. I should extend what I've just learned to make these other blocks random too. One possible idea is to just add more initialization vectors. So come up with another random value, stick it here. Come up with another random value and stick it here. That would work, but it also would require a lot of randomness. So I'm going to do something a little bit more clever. I'm going to realize that this ciphertext is something random. The input was random. The block cipher has scrambled it up. So this is some unpredictable random value. So instead of generating a new random bit string, like a second initialization vector, what if I just use this? That's some random unpredictable thing. So that's what we'll do. This is some random unpredictable value. Why don't we just use that to shuffle up and randomize the second block as well? So this plain text, instead of just being passed through all by itself, it gets XORed with the previous ciphertext block. And you can think of this as another random bit string that we use to XOR with the second block of plain text. So now this ciphertext output should also be unpredictable because, well, that's different every time. So this is different every time. So this input is different every time. Therefore, this output should be different every single time. So maybe you can guess what's coming. We'll just do this again for the subsequent blocks too. This block needs to be shuffled up, so we'll just hook up the previous ciphertext output to the input of this block, and so on and so forth. And if we chain this over and over again, now all of the output should be unpredictable and random. So our goal here was just to say ECB mode is not IND-CPA secure because it's deterministic. I want to add randomness throughout the encryption. So I started with one random value and then propagated it through the entire encryption. So now things should be random. I haven't proven to you that this is correct or that it works. I've just added some randomness. So it turns out this actually does work, and it has a name. It's called cipher block chaining mode because you're chaining up previous blocks to the current block. We could write it as an equation. So you could say, how do you write the ith block of ciphertext? Well, you're encrypting something. It's block cipher output. So I'm encrypting something. And what am I encrypting? I'm encrypting the ith block of plain text XORed with the previous block of ciphertext. So this is just taking the picture and changing it to equations, if you like equations better. And for simplicity, we'll say the 0th block of ciphertext is this IV. You don't have to. It just makes the notation look nicer when you say that this is technically C0. So in English, how do you encrypt things? You first take your message, which could be arbitrarily long now. Doesn't have to be 128 bits. You split it into a bunch of plain text blocks, one after the other, and each one is 128 bits. You compute this random IV, you flip a bunch of coins, and you pick this random value, and then you compute the ciphertext according to this picture. So now we have an encryption scheme. We've introduced some randomness. Now, fair warning, randomness doesn't guarantee security, but at least it's not deterministic. So we have a scheme. Now let's think about decryption, security, and other properties of this scheme. OK, so one property that we should care about is how do you actually get the original message back? It doesn't seem immediately clear that if I encrypt a bunch of messages like this and I throw in all this randomness, that the original message can still be outputted. So to prove to ourselves that the original message can be recovered from the ciphertext, well, there's a couple ways to tackle this problem. One way to do it is with the picture. So if you like pictures, we can try looking at the picture. So let's think about the ciphertext. There it is. You have access to that. One thing I don't think I have explicitly mentioned, but is true, is that you also send the IV as part of the ciphertext. So when Bob receives the message, he receives all the ciphertext blocks plus the IV. You get all of it. So now how would Bob decrypt? Well, he could just run this diagram in reverse somehow. So what would that look like? I would take the ciphertext, and I would pass it through not encryption, because I'm going backwards, but decryption. That's what we see in the decryption picture. You take the ciphertext, you pass it through block cipher decryption. That's the equivalent of working backwards in this picture. And then once you decrypt, well, you're still left with the plain text XORed with the IV. But I want to cancel out the IV. I don't want that. I want the original plain text. So once you decrypt, you XOR with the IV one more time. And remember our handy XOR property. If you XOR this value with the IVs cancel, and I get the original plain text back. So one way to derive this decryption diagram is just to run this picture in reverse. And it works on later blocks too. So for the second block, I would start with the ciphertext. I would run it through the reverse block cipher decryption. That's why this says decryption. And then I still have to XOR out some randomness. And here the randomness is the previous ciphertext block. So when I get this block cipher decryption, I XOR it with the previous ciphertext block. The previous ciphertext block cancels out, and I'm left with the original plaintext. So one way to get this decryption picture is to look at the encryption picture and try and think about how it would work in reverse. Now, if you don't like this, you don't like the pictures, we could also use some algebra to solve it. So for you math lovers out there, another approach to figuring out the decryption equation is to write the encryption equation and then solve for the plaintext. So this is the equation we previously saw, and it represents the encryption picture. And it tells us, given some message and the previous ciphertext, how do I get the next block of ciphertext? Now, if you want to decrypt, you want to solve for m. So we just have to do some algebra and solve for m. So how do we do it? We could decrypt both sides. So I apply d sub k on both sides. And remember, when you encrypt something and you decrypt it, those two operations cancel. So I'm left with this equation. That's good. But I want to isolate m sub I. So I will XOR both sides with c I minus 1. There it is. There it is. Using our handy XOR property, those two terms cancel. And I'm left with the equation for m sub I. This tells me how to decrypt given some ciphertext. So if you didn't like the pictures, algebra is another way you could solve this problem.